All around us, we see the effect of gravitational forces. Suppose I look at this object. I drop this ball, immediately it falls down. Why? Gravitational force. Now I have told you that electrical forces are much bigger than gravitational forces. Then why don't we see the effect of electrical forces all the time, all around us on different objects? That is because most of the objects around us, they are neutral. So even when I bring a charged object near a neutral object, it usually doesn't feel a force. Why? Because point by point you have plus and minus charges. This plus is going to push that plus with a big force, but it's also going to pull this minus with a big force, same force, so these two forces cancel out. Okay? Why same force? Because this distance and this distance, they are the same. At every location where you have a positive charge, imagine the nucleus, the minus charge is, the center of the minus charge is also at the same place. So the distances are the same. Suppose I look at plus minus there, this plus is going to push that plus with a different force, F1, smaller force. Why? Because this distance is more, but it is also going to pull on the minus charge with the same force, F1, and you can see that this F1 and F1 will cancel. It is not that everywhere, every positive charge is going to feel the same force. Each of the positive charges at different locations will feel different forces. But at that location itself, you have a negative charge, which will feel the opposite direction force. And so the plus and the minus, the forces on them, they cancel out. Because the plus and minuses are perfectly balanced, point by point by point. You take every location, plus and minus, they are perfectly balanced. The forces on them cancel, and so the net force on that neutral object is 0. Can I disturb this balance? Yes, I can do that. So all I have to do is to get rid of some of these charges. So let us remove some minus charges. So when you remove the minus charges, this becomes a charged object. Now this plus is going to push that with F and that one with F1. So what is the net force? The net force is in that direction. So a little bit of charging immediately disturbs the balance. That's why you take a straw, rub it on a piece of paper, you have disturbed the balance, you have charged it, and then you can see the effect of electrical forces. Small amount of charge itself will start showing up with large forces because electrical forces are huge. So charging is one way to disturb the balance, and then you can see the electrical forces. So that means neutral objects, because they are perfectly balanced, we don't see any effect of the huge electrical forces. This force and this force, large forces, are perfectly cancelling. One way to disturb the balance is charging. Is that the only way? No. Even by moving charges around slightly, you can disturb the balance. For example, if this was a conductor, you can have electrons moving around. So I'm going to move that minus charge here. And now you see there is a concentration of minus here and a concentration of plus there. You can say that this plus and minus cancels. It has one minus charge here and one plus charge there. How will this cause electrical effects? Can't I say that the whole thing is neutral? Yes, the whole object is neutral, but notice, this plus is going to push that plus with F. It is going to pull this minus with F. F and F will cancel, but it's also going to pull that minus with F. So what is the net effect? F this way. But what about that plus? This plus is going to push that plus, but not with F. It is going to push with F1, a smaller force. Why? Because this distance is more. Right? Now you have a concentration of negative here and positive there. The negative is closer, so the net effect is bigger this way compared to that. And so F minus F1, that is the net force in this direction. So even a small amount of charge separation, we are not even talking about charging the object. We are only talking about charge separation. So the negative charge moved here. If it was not perfectly balanced, location by location by location, point by point by point, this is a charge separation. Then immediately you start seeing that the net force is not 0. There is an effect like this. Am I really saying that you can feel this kind of an effect? Yes, I will show it to you with an experiment. You can see it very easily. To do that, all you need is a can. What can? Soda can, soft drink can. Okay, so this is a metal can. Metal can, basically neutral metal can. It has positive, negative everywhere. But the speciality of a metal can is that the negative charges, electrons, can easily move around, right? So there are huge number of positive negative charges, all equal positive, equal negative. Right now, completely balanced, point by point by point. Every point plus minus plus minus. But if I now bring a straw with negative charge, this is going to push on those electrons. It's also going to pull the positive charges, but the positive charges can't move. The electrons will start moving, so the electrons move that way. Now you see that there is a concentration of negative charges there and a concentration of positive charges here. But what about the total charge? Total charge is still 0, right? Because equal amount of positive, negative. But this will still have an effect, because this negative straw, negatively charged straw, is going to pull these plus charges with a large force. Distance is less. It is going to push on the negative charges with a small force because that distance is more. So what about the net force? The net force is going to be in this direction, and because of the net force, this can will start rolling towards the straw. Can we do this experiment and really see this effect? Yes, let us try that out now. Let us now do a fun experiment using this soft drink can. It's an aluminum can, metal can. Okay, so I'm going to place this can like this. Right now, if I use the straw is not charged. Okay, I have touched it all over, so it's not charged. If I bring it close, nothing happens. But if I now charge it, how will I charge it? By rubbing it on a piece of paper. Okay, so once I charge this straw, you will see a nice different effect. So what is going to happen is, as I bring it close to the can, it starts pulling the can. You can see that I can accelerate the can. I can also retard the can. I can pull it in the opposite direction. So you can make the can roll back and forth like this. Okay, so I'm doing that with a straw, but actually you will get a much better effect if you use a PVC pipe like this. How do I charge a PVC pipe? Right now this PVC pipe is not charged, so obviously there is no effect you can see, right? But if I rub it on a piece of wool, here I have a woolen shawl, so if I rub this PVC pipe on this woolen shawl, it will get charged and it will get a reasonably large charge. And so you will see that it can pull this can really fast, okay, with a large force. So let us see that. Ready? 1, 2, 3. You can see how much force it's exerting. As we just saw in the experiment, this PVC pipe has a negative charge. And this negative charge pushes the electrons here and makes them run off to the other end of the can, leaving excess positive charge on this side of the can. Now these positive charges are closer to the minus charge here on the pipe, right? So the force on the positive charge is large, I'll call it F, and the negative charges here pushes the negative charges there away, but with a small force, I'll call that F1. So the net effect is a force in this direction. This is the net force, which will be equal to F minus F1. Of course, there are also friction forces, etc. to consider, but the main idea I want you to keep in mind is that the electrical force is no longer 0 because F is bigger than F1. Why? Because these charges, we call these induced charges. We also call those induced charges. So these are the induced positive charges. These are the induced negative charges. The induced positive charges near the pipe, they are getting pulled with a large force, whereas the induced negative charges further away, they are being pushed with a small force because the distance is more. So the net force is pulling this neutral can. Notice this can has a total charge of 0. So the can is neutral. And so a charged pipe is pulling a neutral metal can. So neutral metal can is attracted by the charged pipe because the charges induced near the pipe, they are pulled with a greater force. Okay, the further one is pushed with a smaller force. So you now notice that charged objects can attract neutral conducting objects, right? Like this can. So they can attract neutral conducting objects. They can't repel, they can attract. Why? Because if this was negatively charged, it will push the electrons. So that force will be small, this force will be large. If this was a positively charged object, you will get minus here and you will get plus there. So it is going to pull again with a large force and it's push with a small force. It will always attract a conducting object. So charged objects can push and pull other charged objects, but they can also pull neutral metal objects.